Hello, I promised just to provide some narrated slides for you just to cover 2 weeks of the module. Essentially just so that you get a full appreciation of critical path analysis, and also I'll be recording and narrating slides for next week's session, which is on resources management, where we get into smoothing, levelling and crushing. Okay, so this week, critical path analysis. Now I'm not going to run through every slide in great detail, but what I'm going to do is to skim through, indicate the bits that I think you need to know, but then concentrate particularly on the activity on node diagram. You'll be using this and developing this in the case study, which is the Whitbread World Sailboat Race case study. Now this session was entitled Milestone Planning and Critical Path Analysis, and it was really how you set up a network diagram, if you like, a model of the project, and then you add in timings to calculate the total time and identify those critical activities on the network which you have to complete on time. Any delay causes the project to get behind time as a whole. So if we just move through the slides a little, the second slide, introduction to what we looked at, and the readings are in the Mailer textbook, a fairly functional run through some of the areas that we've looked at. Now just a reminder that people use different systems and different methods of developing their diagrams. What you're watching now is my own method, quite commonly used, but Mailer adopts a slightly different way of annotating his diagrams. It's good to know a range of different ones because you'll encounter different ways of drawing network diagrams in the future. Okay, so the first slide just ran us through an introduction, which I've already explained, and we first of all, I introduce you to what was the traditional way of drawing networks, the activity on arrow diagram. Now there's no need to learn this in detail, but the slides I produced here, which I'll flick through fairly quickly, just indicate to you the idea of a network. Almost think of it as a road network, a journey through the project from the first node through to the end node at the end of the project, with the activities represented on the arrows. Okay, so I'll just do these because I really want you to concentrate on the activity on node approach. Now the one thing we did introduce here was the precedence table, and this is really important. You'll face this with the Whitbread case, and the idea is that once you've broken down your project into its discrete activities and tasks and identified and estimated the expected times for those, you should also be in a position to identify which activities have to be completed before another can start. So the precedence table just tells you what the activities are, what the times are in days, and also which activities have to be completed for the next activity to start. And we use this very simple example in the lecture just to represent a simple project, just to get you started on working through a network. Now, one of the reasons why the precedence table is important is because this is the type of format that you input to most computer programs. So for example, the most widely used project management software, Microsoft Project, this is what you do to start generating your Gantt charts and your network diagram, your critical path diagram. You have to input a minimum of what's shown on this page, the activity, the time in days, and then the immediate predecessors. Of course, you can add on extra columns after that to represent optimistic times, pessimistic times, costs, optimistic costs, pessimistic costs for each activity. You could have extra columns indicating how many people are required. Could also be other resources such as what equipment and how much needs to be used. So the precedence table, this is the basic table, but then you can add on extra columns to represent more information about each activity and therefore build a more sophisticated model of your project. Okay, so I'll just skip through. This really just shows you the solution to the activity on arrow diagram. and we showed the forward pass, the backward pass, and identifying the critical path. Now what I'm going to do is spend more time talking through that in detail in the activity on node approach. Okay, so the activity on node approach, and this is the one that most modern computer packages use. It's pretty much the default that people would use in a project. Each activity is represented by a rectangular box, and those are linked by arrows that indicate the order or the precedent in which things need to be done. It allows for more information to be provided and in a more structured way than you found with the activity on arrow approach. Now this is what each node looks like. Now I say different house styles vary, different companies vary, different textbooks vary in what they represent, but this is the one that we will be using. Really each activity represented by a box. You can put a description of the activity in there if you wish, the duration time, the time to take for each activity, and then indicating earliest start time, earliest finish time, and the latest start time and finish time for that activity. And there's also room to put in the total float, or if you like the slack for that activity. Quite good convention is to actually put a shorthand notation or a key, just so that people understand what it is, what the figures mean in each of your boxes, a bit like you'd have a key or a legend to a map or an atlas, just so that people understand the symbols. Okay, so we're going to use that same example, the activities A to F with the time and with the immediate predecessors, and we're going to draw the activity on node diagram. So the diagram looks like this, and you can see that activities A and B can start straight away, have no predecessors. Activities C and D can only start when A is complete. Activity E can only commence when B and C are complete, and activity F can only start once activities E and D are completed. So the precedence table has given us that information. What we're now going to do is actually to fill in the forward pass information. Those figures we've got in there across the top line are the duration or the time for each activity, but we're going to start from the beginning, from the left hand side, and do the forward pass through the network just to calculate the total time taken to do the project. So the first figure we put in at the start, activity A is the start of the project. Start on day 0, takes 2 days or weeks. I'm just trying to remember what it was. Yeah, it was days, so it takes 2 days to complete, and so the earliest that activity can finish is on day 2. Likewise, activity B has no predecessors, so can start straight away. The earliest it can start is at the start of the project, and then the blue figure animating in there is to say that the earliest finish time is day 7. Now we can now move those figures forward. So if we move forward to look at activity C, we can see that it can only start when A is finished. The earliest A can finish is on day 2, so the earliest C can start is on day 2. So I've put that figure in there now. It takes 6 days to complete, so the earliest activity C can finish is on day 6. And you carry on doing exactly the same, moving through the network. So activity D, earliest start is 2, earliest finish is 5. Activity E can only start when B and C have finished. Activity C finishes on day 6, but activity B doesn't finish till day 7. So we have to take the higher figure, because E can only finish when B has finished. It can't start until that's finished. So its earliest start is 7, duration of 2, earliest finish 9 days. And then we just move that forward. Activity F, again the same situation here. F can only start when D and E are complete, but activity E doesn't finish, or the earliest that can finish is day 9. So we put in 9, plus 3 days, and so the total time to complete the project, the earliest the project can finish as a whole, is 12 days. So that's the forward pass. So that's the mechanism of doing that, and actually that calculates the total time for completing the project. Now let's say we want the project to actually finish on day 12, and so what we're now going to do is do the backward pass, but we're going to put day 12 in as the latest finish for the last activity. And that's what you do in the critical path method. You take that time and then you work it backwards using the earliest finish time as the latest finish time. So moving on to the next, that's the information we have in already, but what we're going to do is put 12 in as the latest finish time. So activity F, the latest it can finish is 12. It takes 3 days to complete. So the latest that activity can start is day 9. And then we carry that back. Because that's the latest that can start, that's the latest the preceding, I should say, activities can start. So a 9 will go into both the latest finish times for E and F. So I've done activity E there. Activity E, latest finish 9, duration 2, so the latest start time is 7. Activity D I've filled in similarly. I'm not going to go through every one, but then we can sort of work back from there. Activity B, the latest that can finish is 7, takes 7 days, so the latest it can start is day 0. It has to start straight away. Activity C, again, carry that latest start time of E back to become the latest finish. It's 7, takes 4 days, so the latest activity C can start is day 3. And then with activity A, again we have a choice here. We can take either the 6 or the 3, but we know that the latest that A can finish is 3, because otherwise C will be delayed. The latest start for C is 3. So on the backward pass we always take the lower figure where there's a choice. So we take the lower of 3 or 6, and that becomes 3 minus 2 is 1. So we've actually put in the information there. What we're now going to do is fill in the last piece of information on the node, which is the total float time, or if you like the slack time, and we'll just insert that in now. Okay, so activity A has 1 day of slack. The earliest it can start is day 0, but the latest it can start is 1. So it has a float or a slack of 1 day. You can delay it by 1 day without putting the project as a whole behind schedule. Activity B, though, if you look at that, latest and earliest start are the same. We have to start on day 0. So there is no slack, we can't delay, so that's got 0 days of slack, or if you want 0 days of float in it. That actually signifies it's on the critical path, that you have to start it at its earliest start time, otherwise you jeopardize the whole project being put behind schedule. So if you fill in the other figures in there, we start to see emerge from there that the critical path is activities B, E, F. That's the one where we have to really ensure that activities start and finish on time, because otherwise the project as a whole gets behind time. Whereas the other activities, there is a degree of slack. We can delay activity A by a day without putting the project back as a whole. We can delay activity C by a day. Or activity D, we can delay up to 4 days. Please note, I didn't probably stress this in the lecture, but now you're more sophisticated users of network diagrams. You have to appreciate that if you've used up a day of slack for activity A, then that means that suddenly further downstream that day of slack is taken out. And so activity C, if you have delayed that by a day, that sort of reverts back to a 0, and then activity C suddenly becomes critical as well, because you've delayed it by a day. You're not getting there till day 3, so all of a sudden, because it takes 4 days, it's got to finish on 7. That then becomes critical. And likewise, activity D, delaying a day at activity A, will reduce the float on there by a day as well. It'll come down to 3. It's not on the critical path, there's still some slack, but it means you haven't got as much float or slack as before. So just something to be aware of. Okay, so the critical activities have 0 float. Any delay on the critical path will cause a delay to the project as a whole. Okay, so that's a quick summary of the lecture briefly in about 15 or 16. And in the tutorial, we actually ran through another example, the Park and Ride project. Slightly more, well, not more complicated, but more activities, a bit more to work through, and solutions for that are provided. And also in the mailer textbook, there are some other examples for you to work through if you wish. Okay, so hopefully that's given you a quick review of the critical path method.